welcome everyone. It's a great pleasure to introduce Neil Walton from Durham University. Neil received his PhD from Cambridge. He then worked at University of Amsterdam, where he also held a prestigious Veni Fellowship. He then worked at University of Manchester, and he's finally now a professor in operations management in the Durham Business School. Neil has done a lot of very important work in queuing and in applied probability in general, and he's won many accolades for his work, including Best Papers Awards in Sigmetrics and an Erlang Prize from the Informs Applied Probability Society in 2018. And today, Neil will talk about MaxWeight, scheduling, and learning. So please, Neil, I look forward to your talk.
Okay, great. Thanks, Steve, and thanks to the organizers for having me. So yeah, it's a bit of a sort of several talks or several different topics, starting with MaxWeight, talking a bit about scheduling in general, and then from MaxWeight leading into kind of learning a little bit and some work about learning in MaxWeight, and then some work about learning on its own, and then some work about how queuing can help with some sort of learning results potentially also. So this is sort of a bit of an outline for the talk. As you can see, I've got like 75 slides here, so I might run out of time. So we hopefully get through topics 1 to 4, and if we've got time, get through topic 5 as well. So the first part, I'll talk about some sort of older work with Maury Bramson on MaxWeight and its stability and its instability properties. So probably focus a little bit more on instability properties of MaxWeight. Then I'll talk about essentially an observation about how MaxWeight can be seen to be one way, an implementation of a result called Blackwell's approachability theorem, and how maybe some of the reasons that the stability properties that you get with MaxWeight hold because it's sort of essentially implementing a Blackwell type policy. But the Blackwell approachability itself leads into this kind of area of online learning. And so I'll talk a little bit about some ways, some sort of quite a bit older work on kind of online learning and queuing, which I did a little while ago. And then more recently, I've been working with Louisa Rebuffy, who's a French PhD student, on online learning and revenue management in queuing systems, and some results around that. And then finally, I'll talk, if I get time, I'll talk a bit about how some results that we use in queuing, specifically some bounds by Hayek, which are kind of similar to Kingman's bound, could be used perhaps to help get some results on stochastic approximation, which is also used in kind of the learning area. So sort of rather than how can learning help queuing, but how can queuing results help learning maybe a little bit as well, stochastic approximation. Okay. So that's sort of roughly the agenda. Like I say, I'll probably run out of time. I've got my watch here, so I'll keep an eye on the time as well and see if it can tell me also. So we'll just kind of go through, and there's a few different topics. So yeah, okay. And feel free to jump in with any questions or anything as we go along. Okay. So yeah, like I say, the first part is on MaxWeight and stability instability. This is a result, a paper that appeared in Math Over Wire in 2021. It's with Maury Bramson and Bernardo Doria. And the idea is to study MaxWeight within the set of models which are known as switched queuing networks. So I explained a little bit what a switched queuing network is, and then I'll explain what MaxWeight is, and I'll explain why MaxWeight tends to be can be a good policy for switched queuing networks. Okay, so a switched queuing network is something like this. It's where you've got a set of queues, and there are servers, and there can be constraints on which servers can serve simultaneously. And these can be quite general constraints, but in this specific picture, I've done it in a way where if there's a line between two servers, then I can't serve them simultaneously. I can't serve a job from this queue and this queue simultaneously. Okay, so I have a discrete time model, jobs arrive, and then I can make decisions about which servers to activate in order to try and serve the jobs that are there. Okay, so in this case, this isn't allowed. I can't try to serve from this queue and this queue at the same time because these guys have a line between them. Okay. However, something like this is allowed, where there's no line connecting these two servers, so it's essentially allowable for me to try and serve from these two queues, and I decide that I will use that schedule. and then a job departs from each of the two queues, and then we can continue like this. Okay, so jobs can arrive, then we come up with invisible schedules, and eventually, hopefully, keep the queue sizes low. Okay. And it's a non-trivial problem, essentially, to stabilize one of these systems or come up with scheduling policies based on the queue lengths in order to stabilize the system. Okay. And the type of model I've just described here is this, what we call a single hop switch network. So the idea is that we've got, say, our scheduling constraints and our queues, and as soon as the job is served, it essentially leaves the system forever. Okay, so it doesn't move between different parts of the system. Now, that's kind of a reasonable first cut model, but these sort of switch queuing networks typically use the same model as, say, wireless networks, where the lines between these two servers might correspond to some sort of interference between the different, say, Wi-Fi routers or something like this. Okay, so in a communication network, obviously, naturally, things communicate that essentially the jobs might move between the queues. The same would be, say, in a manufacturing setting, that you might move inventory from one place to the next. Okay, and so it's natural to think also as well as single hop switch networks. It's also natural to think of multi-hop switch networks. So here we might have routes through the system. We have a red route, and we have like a sort of yellow route here, where the jobs will move from one place to the next. Okay. Okay. Is that model reasonably clear to everybody? Okay. Okay. So then I'm going to talk about one specific policy for switch queuing networks, one which is called MaxWeight, and I'll discuss a little bit about its stability properties. So I'll give a little bit more model notation here. So we'll have a discrete time model. I'm going to let J index the set of queues, and AJ of t is going to be the number of arrivals that occurs at time t. The QJT is going to be the queue size at time t for QJ. I'm going to let S be the set of schedules, which is essentially the number of jobs that I can serve from the different queues in a given time slot amongst a set of admissible schedules, the ones that are allowed. And then DJ of t is going to be the number of departures or the schedule I actually decide to implement at time t, and the number of jobs that are taken out. Okay. And MaxWeight is essentially the policy that maximizes the sum of the queue sizes served. Okay, so you can see that essentially for this diagram here, where these interference constraints, there's two reasonable schedules. The first one would be that I serve from this queue and this queue. Okay, and the other one is that I serve from this queue and this queue, which I've highlighted in green. And the reason is the green schedule is kind of better than the white schedule here, is because, well, if I sum up the total number of jobs in the system, I'm essentially allocating work to 4 queues that consist with 4 jobs in total compared to 2. Okay, so then and if we generalize that up, essentially what we want to do is this: we want to look at the departure rate times the queue sizes that maximizes this sum. Okay, and we maximize that over the sets of schedules that we can do, and that gives us the departures that we should take out of the queuing system. Okay, all right, and so that policy that we end up with is called the MaxWeight policy. Okay, and a kind of fairly simple example that I'll mention about a little bit later would be where if I had lines between all of the servers here, this would just simply mean that I would, if each server is linked up like this, for example, so it's a complete graph, we'd always just be serving the longest queue. Okay, so that'd be a simple special case. Okay, so it seems to be doing something fairly rational in terms of serving the longest queue. Now, a question that one can ask is, when is any policy, including the MaxWeight policy, going to stabilize the queuing system? And by that, I mean either that the queue sizes can be driven to 0 so that the departure rate is equal to the arrival rate, or that simply, or in a more specialized case, can we make say, if you had a Markov chain model of this, can we make that Markov chain positive recurrent? Okay. And so this is essentially what we're going to describe here is what sets of arrival rates can we potentially stabilize? Can we potentially keep the queue sizes bounded? Okay. So I've got a special type of switch network here. We're going to have like a server here that is devoted only to queue number 1. And I've got a server here that's only devoted to queue number 2. And then I've got like a flexible server here that can serve from both of these queues depending on what I prefer. Okay. And so, so for this, there's essentially in this picture over here, I've written out in the circles, the sets of schedules which are available. I can do nothing. Okay. I could do this, which would mean trying to serve 2 things from the first queue and doing nothing in the second queue. Or I could do this thing over here, which is probably the most sensible choice at the moment, would be to serve 1 thing from this queue and try to serve 2 things from this queue. So this and this, okay? And then I can just draw down all of those dots, and those are essentially all of the departure rates that I can do in 1 unit of time, okay? And obviously you can imagine that I could, over a longer period of time, I could average, I could choose to take the average of these two scheduling choices. So if half the time I did this schedule and half the time I did this schedule, I'd end up with a departure rate on average, which is here. Okay. So then essentially the sets of departure rates that you can support is essentially the interior of the set of schedules. I just kind of color in the region here. Okay. And since those are all the departure rates that I can get, to keep a queuing system bounded, I need the average departure rate to be higher than the average arrival rate. So anything where there's an arrival rate where I can find a departure rate that's above it is something that I can stabilize and keep the queue sizes bounded. Okay. And so this defines essentially both the sets of average departure rates I can support, but also the sets of arrival rates that we can stabilize the system with. Okay. So the gray region here is sometimes called the stability region. Okay. It is the sets of departure rates that if I was given the arrival rate, I can find a departure rate to stabilize the system. Okay. All right. So the stability region is if I'm given the arrival rate, these are the sets of departure rates which I can use to stabilize that. Okay. Which is different to like something where if I'm saying I'm given, can I think of a policy that even if I didn't know the arrival rates, I can still stabilize it. Okay.
Yeah, I have a quick question.
Yeah.
Would this model still be considered as an input switch model, or it's a different queuing model?
It would still be a switch queuing network. Yeah, it would be. Yeah, yeah. Okay. It would still be within that class. There's what are called input queue switches, which are a specific type of switch queuing network, which are for internet routers. But this would still count within the set of switch networks. Yeah, 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 correct. Yeah, yeah, yeah. Okay. So anything where there's sets of schedules, I don't need to have to draw these lines in between things. It's just anything where I can choose the number of servers and there's constraints on which things I can do at each time. Yeah. Okay. Thanks. Yeah, great question. Yeah. Any other questions? Okay. All right. So now we know the sets of things we could stabilize. Now, the cool result about MaxWeight. So in principle, to be able to stabilize, I'd need to know the arrival rate, and then I could work out the departure rate and then stabilize the queuing system. Okay, but the cool thing about MaxWeight is you don't need to know the arrival rate. It will just stabilize the system anyway. Okay, so the famous result of Tassius and Inframides in the sort of early 90s is that MaxWeight is able to stabilize for all arrival rates within the stability region. Okay, so I don't need to be told what the arrival rate is. I can stabilize the system and always get the best stability that I can out of the system. Okay. And then this result was kind of developed further by McEwen and John Walrand, Venkat and Thoerem, where they essentially applied this to internet routers and showed that you could get maximum throughput through an internet router. So that sort of popularized this policy quite a lot in terms of sort of design of core internet switches. Okay. And the proof's very simple. I won't go into too much detail, but essentially you just it's a Lyapunov function based proof where you take the sum of the squares of the queue sizes. You look at how that behaves on average, how the queues evolve on average, and then you just basically apply chain rule. And then you do to the drift of the Lyapunov function, you try to basically try to get that to go down as much as possible. That's essentially the proof. So it's kind of like a couple of lines of proof, essentially, the main ideas. But don't worry too much about that. I won't go into too much detail. But basically, it's a quadratic Lyapunov type argument. That's a useful thing to remember. Now, that's quite a popular result. Maury Bernardo and I wrote a paper about proportional fairness and showed that it could work on multi-hop switch networks. So just to say one quick caveat is this result here would only apply to a single hop switch network. But the question we were asked is, does this apply to multi-hop networks? So things where jobs get communicated between the different queues. And, you know, although MaxWeight has this nice stability properties for single hop networks, it actually doesn't when you go to multi-hop networks, or when things move between different queues. Okay, so you know, the interesting thing is, yeah, so MaxWeight, like I say, has been studied extensively in the context of communication systems. However, in communication systems, obviously the jobs and the packets, the information gets processed through different queues. And so it's natural to want to understand how MaxWeight might work in a multi-hop setting where you've got routes in the system. Okay. And you know, so the question we might ask is that still maximally stable or not? And basically the answer is no, that you can come up with counterexamples. There was an earlier counterexample by Matthew Andrews using sort of adversarial queuing to show that it might be unstable. And then we sort of came up with the kind of what I'd count as sort of the first proof of this, that actually you can come up with examples where you apply MaxWeight, and if things start to move between different parts of the system, then although it's got nice stability properties in the single hop setting, it doesn't in the multi-hop setting. Okay. And the way it works, like the way the counterexample works is it's very similar to the kind of Rybko-Stolyar. So it's basically kind of Rybko-Stolyar network. So the idea is that you start with one set of queues very busy. So this area over here might be quite busy. Let me change the color. And the other area, you keep it fairly empty. And if we apply MaxWeight, if these queues are approximately equal to another, what's going to happen is it's going to spend a lot of time sending stuff over here and then some of the time serving stuff here. Okay. And if we get the numbers right, what's going to happen is essentially we're going to flood up this B0 queue. It's going to get busier and busier and busier as this part of the system drains out. And this is going to get busier and busier, but not quite as fast as this queue. So essentially what's going to happen is we're going to be only processing work in this direction and essentially not processing very much in this direction. Okay. And so then what's going to happen is we're not going to be fully utilizing. So in the same way the Rybko-Stolyar network works, is you sort of do this, and then you do this, and then you do this. And at each iteration of that, the net queue size of the whole system grows. Okay. One of the reasons I think that's kind of an interesting result is because a special case of MaxWeight is serve the longest queue. So in addition to MaxWeight in itself being interesting, so the way in my head I kind of think of this example where, you know, you've got maybe several queues over here funneling into one area, and you've got several queues over here funneling into one queue over here. It's something like this picture over here. So imagine like I've got some road traffic junctions here, and all the vehicles that arrive here are going to get, sorry, this is UK, so we drive on the left-hand side of the road. So all the vehicles that join here get funneled in and then move over here, and all the vehicles that arrive over here get funneled in and arrive over here. And then at each local traffic light, we do the natural thing that you think you should do. You just, if you can only serve one junction at each unit at a time, you just serve the longest of them. And basically what this says is even if you do that, you basically always try to serve the longest queue, you're still potentially not going to get the best stability region out of the system, that actually there are policies that would have stabilized the system and this one doesn't. And so like you see that kind of, you know, even though when I'm like teaching like to the MBA students here in Durham, which I just started doing, you know, say like deal with the longest queue, that's where the bottleneck is, that's the issue, and you should try to maximize the processing of that part of the system. Actually, that's not what you should do if there's sort of routing between the different parts of the system. Okay. So what that shows, the surprising most obvious policy there is actually a bad idea when it comes to getting the most stability or the best processing speed out of the system. Okay. So then we started to look into how you might fix the stability issues with MaxWeight, and how could you get it to work for multi-hop networks. And the sort of solution that one comes up with is not ideal, but it's probably, there are some sets of systems where it could still work. So it's possible to adjust the MaxWeight policy to achieve stability or positive recurrence when you've got multi-hop networks. So the easiest way to do it is if you know what the load is, if you divide your departure rate here by the load on all of the queues, then essentially it fixes everything and you can make it stable. Okay, so the policy implemented here, if I put that into a network, would still stabilize the system. Okay, and that's sort of one of the reasons why I like proportional fairness. It's just where you take a logarithm of this guy, and the reason the logarithm doesn't care about the load anymore is because that's going to separate out from the optimization, essentially. So there are ways of fixing it, but then you need to have some sort of estimation of what the loads are on the different parts of the system, which then is not what MaxWeight's about. One of the selling points of MaxWeight is you didn't need to know the arrival rate, and this is saying you need to know the arrival rate. Now, I would argue that there are still advantages to implementing something like this if you do know the arrival rate, because even if you take the best policy that's static and you compare that to an adaptive policy, the adaptive policy will usually have much lower queue size and less delay. And so this will be still adjusting to the parts of the system where there's pinch points, essentially. So potentially would have a better performance than the static policy where you know the average arrival rate. Okay. Right, and the proof, I won't go through the proof too much, but it's sort of like you use the MaxWeight policy itself as a Lyapunov function, and then things work out. I should also add briefly that there are policies where the loads are kind of fixed as well. So if you have something where things branched out, or you have things along in a production line or something like this, then the arrivals are fixed all the way through. And so you just need to know the average processing capacity. So there will be specific networks where this you naturally know what this is anyway, and it doesn't affect things. Okay. Two sort of practical extensions that I've been working on a bit with some co-authors. So Hai Vu and Te Huang, who are both work in transport systems in Australia at Monash University. We've worked a little bit on given that you need to kind of estimate a weight associated with each part of the queuing system, then we've been working a little bit on models where you essentially associate a statistic with each job that gets processed into the queues, and then you could basically try to learn what the different parameters are associated with the weights at the different junctions. And that gives you sort of one practical extension, given that you need to learn the arrival rates, where you can essentially improve the performance of the scheduling policy. And that seems to work quite well in practice. So we apply that in sort of like some road traffic simulation situations and things like this as one way of sort of, given those adjustments, getting something that works well on a network, but also is able to cope with, say, vehicles that speed up and slow down. Some other work that we've been doing is rather than using queue size as a proxy, using things like delay as a proxy here. And this is, so basically try to look at the delay divided by some target that you might have, say, for waiting times. And this is, so you can imagine, well, I work a bit with the NHS, I have like a contract with the NHS in Manchester, and I've sort of been proposing this as part of like a data system that we report up to the NHS Trust in Manchester, where they look at they essentially do we recommend to do things like MaxWeight, where it's adjusted according to the priority levels of the different patients, and then we can use that for making recommendations on where the operations get moved to around the different trusts. Okay, so those are two sort of small extensions. They're more on the applied side rather than the theoretical side. Okay, so that sort of ends the first part on MaxWeight proving. Yeah. Yeah.
So I have a few questions. I guess, is MaxWeight the same as maximum pressure in this setting, or?
So great question. So yeah, so I wasn't going to talk too much about back. So there's two. Yeah. So let's talk about that. So there's two policies. One's MaxWeight, and that's where I just maximize the sum of the departure rate times the queue size in a network. Okay, and there's another policy called back pressure. And by that, what I mean is if I've got a network where I've got two queues, rather than using just the queue size here, what I'm going to do is I'm going to look at the difference of the two queue sizes between the upstream and the downstream. And that defines a new weight. I think I remember rightly, it's the difference of where I think it's upstream compared to downstream. I probably might get this wrong, but you basically look at the departure rate, and I think it's compared to the next hop afterwards, like this, and that would be what back pressure tells you to do essentially. That's the same thing that quadratic Lyapunov function will tell you to do at the beginning. Now this works for multi-hop networks, but you do need to have quite a clear view of where everything is going in your system. So that's practical when you've got a small number of queues, but when you've got a very large system, it tends not to be as practical for those types of problems. But back pressure is a great policy for that kind of multi-hop setting as well, if you see what I mean. So there's two main solutions for dealing with stability in the multi-hop setting. One is to do back pressure, in which case you need to know all the classes. Or the other way is that you take a logarithm here, take a logarithm of the departure rate here and then times that on, and that's the other way to deal with it, which you don't need to have such a big state description for the system. Okay.
I see. And is the back pressure also have the same stability issue as the MaxWeight you brought up?
So no, the main issue with back pressure is the scaling up of the size of the problem. So the optimizations involved get quite large, and you need to have quite explicit description. So if we implemented back pressure in the internet, we'd need to know where every single packet was going to and all the routes, which is massive. So that's why you'd use MaxWeight in an internet router, because you just want to use the local information of the queue sizes. You don't want to know the exact route specification and maintain a queue for each route of where things are going through your system, essentially.
I see.
Okay. Yeah. So there are two main solutions, but because MaxWeight is used in those sort of internet router situations when there's low information overhead, then that's one of the reasons why. But also, like in principle, if we really wanted to apply pure back pressure in this road traffic situation, we'd need to know where the cars are going. In principle. Now, there are ways of going around that. You could say probabilistically, I might know where the cars are going and things like that. And in that case, you might be able to get around it a little bit. But yeah. Okay. Right. Are there any other questions? Okay. Yeah. Hey, Dave.
Hey, Neil.
Hi.
It was fun to catch up. So I guess the weights in the version of MaxWeight that's stable, is it true that the weights need to know more than MaxWeight would otherwise have needed to know?
Yes, correct. Yeah.
So is there an impossibility result out there that like you need to know stuff to stabilize in the kind of hopping around case?
I don't think there's like an impossibility result. There are things that are known that can work in the multi-hop case. But
what's the minimal, what is the least that we need to know to stabilize in the multi-hop case?
Yeah, I think that's a great question, and I don't know the answer to that. It seems to be that the types of things that work are doing something closer to processor sharing, they're doing longest queue first, or they're using a much more explicit state description, but there's not a known minimal set of information in order to stabilize one of these systems. It is a great question. It's also difficult to know if you can do things like priorities for the different queues and things like this, and so there's a few questions like that where at least I don't know that if the answer's known anyway. No, it's a great question. I wish I knew. So it's another question.
Hi. Am I audible? Hi.
I can hear you.
Yeah. Okay. So there has been another line of work where they have used notion of shadow queues to I think by Stoller. Right. And there is yet another work where they show that you don't need back pressure if arrival satisfies some regularity condition. Right. I think how do these approaches compare to those based on, say, on shadow queues?
I think Sasha was on here earlier. I was not sure if he's gone now. He was here a minute ago because he could have answered that. I mean, that in general, in terms of the shadow queues, what they're doing is that the stability regions is essentially constraints, and then for each of those constraints, you're basically storing a queue. And that as that constraint gets closer to being violated in terms of the stability region, then you're essentially implementing a policy to basically bring that constraint back down again. So that's the main difference, if you see what I mean. Whereas these are just going purely for stability. With the kind of shadow and virtual queuing things, you're aiming for another optimization, and as a constraint starts to get violated in your scheduling set, then you start to use these queues as Lyapunov functions to try and bring that back part of the system back down. So that's my sort of understanding of how the kind of shadow queues work with this kind of work. So it's aiming for a slightly different objective, same for like an optimality objective subject to stability, if you see what I mean. Yeah. Does that answer your question?
Yeah. Thank you.
Okay. Good. All right. So I'll talk about like a second bit of work. So I'll talk a little bit about, so I've spoken about MaxWeight and its stability, its instability sometimes in networks. We discussed a little bit about some alternatives as well for dealing with networks and a few extensions that lead from that. This part I'll talk about connections between MaxWeight and Blackwell's approachability theorem. This is more of an observation rather than like a theorem or a result. I sort of knew about this a little while ago, mentioned about in a paper in 2014, and then I decided to kind of write it up into this tutorial that was in I think it's 2021, so the latter part of 2021. And I think it's it explains a little bit why, so maybe to get back to Dave's question, it explains a little bit why MaxWeight doesn't need to know the arrival rates, but maybe would need to know things like service rates. And so gives some indication, it's not a proof for but gives some indications to why MaxWeight doesn't need to know arrival rates in order to stabilize the system. Okay. So there's a very old result from the 1950s called Blackwell's approachability theorem, and it's essentially about how you can guarantee some vector, the average of some vector that you take, can be made to approach or get close to some convex set Z. Okay. And it's essentially a vector version of the zeros of a two-person zero-sum game. Okay. And if you think about, one way to think about what a zero-sum game is doing, it's sort of saying like, if this person does this, then I've got a best possible action. And the minimax theorem says that no matter what action that other person does, I can always do this action and it benefits me, if you see what I mean. And that's the same thing as what MaxWeight is doing. MaxWeight's saying that like, if I knew the arrival rate, then there's a policy that I can implement to stabilize the system. That's what the stability region is defined to be. And what MaxWeight is doing is saying, well, regardless of what the arrival rate is, I've got a policy that I can always implement that takes me towards the queue sizes being 0. And so essentially it's sort of in its statement is doing the same thing as this kind of two-person zero-sum game, but on vectors. And so it's still got that kind of property to it. So Blackwell's approachability has been sort of more popular in recent years because of its use in online learning and online convex optimization. And in fact, the two are actually equivalent to one another. Whereas the aim here is just to discuss essentially why you can think of MaxWeight and rack pressure, which Jane mentioned about, could be thought of as special cases of Blackwell's approachability result. Okay. So explain very briefly, I kind of explained verbally, but I'll explain briefly what Blackwell's approachability theorem is. So it's a classical result in learning and control. And like I say, it's a vector generalization of the minimax theorem for two-person zero-sum games. The setup's as follows, that you can make some decision D, which here I'm thinking is departures, and you've got an adversary who makes some decision A, which I'm thinking of as arrivals into a queuing system. And then you get, think of this as being a matrix where each component of the matrix is actually a vector. Okay, so Rij here is a vector. And I take a kind of weighted combination of my decision and the adversary's decision. Then out of this, I get some vector, capital R. Okay. And what I'm going to store up, which I think of as like the queue size, is just the average of all of the rewards that I've collected up. Okay. And we say that a set Z here is approachable if I can find a way to make a sequence of decisions, D, where no matter what the adversary decisions are, A, I can get arbitrarily close to this set Z. Okay. So that's sort of the definition of what approachability is. Okay. So we're going to make a sequence of decisions, and the adversary is going to make a sequence of decisions, and no matter what the adversary does, I can always guarantee you getting close to this set Z. Okay. And Blackwell proves the following are equivalent. The set Z, I think Z has to be convex here. The set Z is approachable if every half space containing Z is approachable. So that's this condition here. Or even better, that no matter where I am in terms of my average queue size here, there's a decision that I can make here that sends me to the other side of, on average, of that half space. Okay. So if I'm here at Q, there's a decision that I can make D of T that no matter what this A is, I'm always on the other side of this line. Okay. Where this line is just the line projecting my Q down onto the set Z. Okay. All right. So that's essentially the way the result works. Perhaps unsurprisingly, given what we saw with MaxWeight, the result is sort of essentially a quadratic Lyapunov type argument, where you expand that out and then look at what implement this decision at each stage and then stabilize the system that way. Okay. It's used in online learning, so moving away from queuing, but in online learning, there's kind of people do lots of things to do with like regret minimization. So I'll mention very briefly about that. So here you have kind of discrete time. Each time you can make a decision as to where you're going to, say, put your money. Okay. So you decide, am I going to put all my money in option 1, option 2, option P or N? Okay. And then for each of these, you receive some reward, which is sort of the size of the gray box here. Okay. And I can choose between a fixed set of decisions as decision 1, decision 2, or decision P. Okay. And my policy is essentially each time I'm going to have some distribution over the sets of decisions. I'm going to maybe concentrate that probability on the thing that I think ultimately is the best long run decision. Okay. So you can see here that this option P seems to have higher rewards, say, than option 2 and option 1. Okay. So you'd hope that a good policy would start playing things at random and then eventually start to concentrate down on the Pth option. Okay. And so the aim for this simple kind of online learning setting is to find a sequence of decisions, which is how much you put in, how much of your weight or probability you put in each of these boxes. That's going to be as good as the best fixed decision. Okay, so the aim is to find a sequence of decisions as good as the best fixed choice. And the interesting thing is you can do this without any statistical assumptions on the sizes of the rewards here. Okay, and then the regret, which is used a lot these days, is essentially the difference between the best individual decision compared to the sequence of decisions made by your policy. Okay. And something is said to be Hanan consistent, or have no regret learning if this is little or O of t. Okay. So if this is small in terms of t, then that essentially means you're doing as well as the best fixed condition. Okay. All right. And what Blackwell showed in 1956 in a kind of follow-up paper to his original result is he proved that you could come up with that, use his result to come up with what's called Hanon consistent policy. Okay. And the way that works is very simple. You look at the vector of regrets. Okay. So the regret of paying action I compared to my policy all the time. And he said that if I knew in advance all of the actions that are taken, I can always choose this point here that's on the other side of this plane that belongs to the kind of negative orthant. Okay. And so for that, remember that Blackwell's result said, when I project down here, if I can always find a point on the other side of this line, then I can, regardless of the action A that's chosen, then we're fine. Okay. And so from that, you can apply the Blackwell result, say it's approachable. So this regret vector is eventually going to move towards the negative half plane, which is another way of saying that it's got sublinear regret. Okay. So that's the way the proof works there. So that's a result called the Hanam-Gadam theorem that was proven by Blackwell. And the point is that you can do the same sort of analysis with MaxWeight, or look at it within the same way, that we can have a picture from before with the arrivals, the queue sizes, the service schedules, and the decisions here, and think about what MaxWeight does in terms of its decision. And here's just the Tassus and Ephraimides result again. But we can get a very similar picture that the queue size is a vector, and we could think of the average queue size as a vector, which is the sum of the arrival rates minus the departure rates. Okay, so we could think of the queue size as a vector of arrival rates minus departure rates. And so for that reason, it would fit within the kind of formulation of Blackwell as a kind of average of the queue sizes. And you can always find this point here, which is essentially the average arrival rate minus the departure rate, which maximizes the difference with this plane, as this point over here. Okay. And because whenever I project the queue size down to here, which is the plane with queue sizes as a normal vector, because I always have a point on this side of the plane whenever it's within the stability region, then I can always find a solution on this side, and thus I can always find a way to approach this region. Okay, so you can think of that. The reason that MaxWeight doesn't need to know the sets of arrival rates is because it's implementing an approachable policy. It's implementing a sort of zero-sum game policy where no matter what the arrival rates does, it's always moving towards the stability region. Okay. And the same thing holds for back pressure as well. You could still argue that way. Okay. And like I say, it's not a radical change in terms of the proofs or anything like that. So that's why it's in a tutorial rather than anything else. It's more like an observation that this is actually maybe the reason the MaxWeight's doing what it's doing is because of this kind of Blackwell way of thinking about things. Okay. Okay. But essentially the kind of results of approachability imply MaxWeight stability properties, that it's always able to stabilize whenever the arrival rate belongs to the scheduling set. Yeah, Dave?
Could you remind us, Neil, because I remember finding it striking, why is it again that like the normal like reflection nuisance of queues doesn't manifest here? Why it is just a linear dynamic when you think about it this way? Because right at a high level that, you know, one might think, oh, like queues are not kind of linear in some sense. They have some kind of max plus thing, and so these kinds of
I mean,
and I remember
this case, you have to be a little bit
finding
careful here. So you can think of the queue size as the sum of the arrival rates minus the sum of the departure rates, the departures, and you have to be a little bit careful with the proof that if one of the queue sizes is 0 and we take this here, then we don't have to make an option that takes us in this direction. That's not a valid move because the queue sizes go negative. If you see what I mean. So you have to be a little bit careful if one of the queues is 0, that we can still make a valid move that takes us inside this this region here, if you see what I mean. So is that what you're meaning in terms of the question, or maybe I'm getting into another technical detail?
I was just asking just to comment on that, because I remember like of the steps, because it's not a long argument in the tutorial that it's here. It's very nice, and I remember just thinking that was the part where, you know, I thought it was kind of quite interesting, because because that reflection is often what makes analyzing queues so hard in some sense, and here it just doesn't even manifest. It doesn't.
Yeah, I mean, it doesn't manifest in MaxWeight anyway, because you don't ever have to make a decision that's going to let any of the queue sizes go negative, and it's the same here when you're applying the Blackwell results. There's a little bit of like a borderline issue there. But also, you need to be able to write this out as a kind of matrix thing. So you need like an identity matrix and a minus identity matrix, and then the departure. So you have like this. You need to be essentially applying that vector and that vector to this matrix here. Okay. Yeah. Okay. Yeah. Sasha.
Yeah. Hi, Neil.
Hi.
Can you quickly comment? You know, so this proposition 1 is rate stability, right?
Rate stability.
You're saying it's an easy additional step to just get, you know, usual
rate stability. Yeah. Exactly. Yeah. So not proving positive recurrence or anything particularly fancy here. It's more of an observation that if we look at it through the eyes of Blackwell's approachability theorem, it seems sort of clear from that result, or it's a corollary. You can see as a corollary of the Blackwell result as to why MaxWeight has its rate stability properties, if you see what I mean.
Yeah, but formally speaking, so if all I know is, you know, results of Blackwell from the 50s, right?
Yeah.
I can, you know, and I know them now, right? Or in the 90s.
Yeah.
I can easily adjust it to actually get positive recurrence, right? Or there is some work involved.
I can easily adjust it to get rate stability.
No, rate stability, I see. Rate stability,
and you could probably adjust this argument and say there's some positive epsilon here, and then apply Foster-Lyapunov or something instead. Yeah.
Okay.
Yeah. But the point here is that this is rate stability where, you know, I could adversarially move, you know, this is more like the kind of Neely results where you can adversarially move the arrival rates around over time as well, if you see what I mean. So it's a little bit stronger than positive recurrence in the sense that I could actually have the arrival rate in one area of the stability region and then move it to another area of the stability region and still have the rate stability, if you see what I mean. So there's got that aspect to it. Yeah.
All right.
Okay. Yeah. Again, it's more of an observation than anything else there. So okay, yeah. All right. So the point there is to say, so just as classical results in online learning can be seen as a consequence of Blackwell's approachability, so the idea of kind of like the way you can get online learning results from Blackwell, we can see that also classical algorithms potentially, such as MaxWeight and back pressure, can also be seen as a consequence of Blackwell's approachability theorem. Okay, so there's this kind of connection between online learning and queuing. So one of the things we've been working on a bit more recently is some links between online learning and queuing. So this is originally appeared in 2014 and developed a slightly different version in 2021. So MaxWeight is stability is achievable with unknown arrival rates, but however, it's not true for service rates because essentially in that matrix, we need to have the service rates inside the matrix. So we can consider the impact of online learning on service rates. So kind of in sort of 2014, I wrote this paper where you kind of have online learning and queuing systems. And essentially the point is that at each time, you have a number of service modes that you can choose between, and those might have different service times. And essentially what you want to do is essentially experiment with the different service modes that you're choosing between, and then essentially narrow in on the service mode that's the one that's best at processing work through the queuing system. Okay. So the idea is like, well, if you know the regret of the algorithm, how does that regret impact the queue size process essentially? So if I had an algorithm with a certain regret bound, how would that help in terms of keeping the queue sizes low? Okay. So the idea is to have a policy pi that has some regret in terms of learning the service, and it has a regret with respect to the service times, where tau here is the amount of time it takes to serve a job. And then you have some arrival process. And then for like a GG1 type queue, you've got things like Lindley's recursion, which relates how the queue sizes goes compared to the service rates. Okay. And the nice thing about Lindley's recursion is you can kind of sum up arrivals and departures in a very similar way to what I was describing earlier. Okay. And what you can show is that if you knew the last time that the queue emptied, then the difference between the policy that you implement, that's like the online learning policy, and the optimal scheduling mode is essentially determined by the difference of the regret of the two algorithms between when it last emptied and current time. Okay. So then that means if you've got sublinear regret, then you're going to essentially have sublinear. If you've got a sublinear regret algorithm, then this should be little o as well. And so then you should be, and if your optimal policy is stable, then you're going to also achieve stability of your policy. So if you've got a good policy and a good learning algorithm, then you can guarantee that you get a good policy out overall. Okay. So an example of this would be to apply like a stochastic bandit algorithm to a positive recurrent queuing system. So the difference between these two times would be little o of 1. And if it's like a bandit algorithm, you'd have like a log of t regret. And so what that kind of lemma would say is the difference between your policy and the optimal policy would be about the difference of these two logarithms, which would be about order 1 over t. Okay. So that's essentially a version of the result that this Chris Manathi and others have like a paper on that kind of setting. It's kind of stochastic bandits and queues. Okay, so you can sort of see how the kind of, if you get a good regret algorithm, you can get a good queue size performance also. Okay, to give us like the sort of more involved example, but this is from the tutorial. So you could imagine something like this, that you've got like a call center, and then people call up and they've got jobs and they've got like a context associated with them. And you can decide, I'm going to serve them as like a type plus job or a minus job. So I might decide the way I'm going to essentially answer the call under these two service modes, given the information that I've got about the customer when they come in. Okay. And you can have it where a policy is a map between some weighting that I have, where I weight the different contexts associated with the caller. And if it's a positive context, then I give it a plus and serve as a plus job. And if it's got a negative context, then I serve it as a minus job. And you can have it as the following. If I guess from the context the right way to go about answering that telephone call, then I get fast service. And if I incorrectly guess the context, then I get slow service. Okay. And this is quite a classical kind of algorithm. This would be sort of like applying the perceptron algorithm or applying that kind of setting to a kind of queuing model. So you're trying to kind of guess what's the right way to kind of serve this customer based on doing some sort of like, well, basically like a kind of like a separation. So yeah, a famous example of this for solving this type of problem. So you can think of this as like, we've got pluses and minuses. We're trying to essentially come up with a weighting that separates the pluses from the minuses out. Okay. And one way to separate them out is essentially to apply a kind of version of gradient descent to that. Okay, so that's the learning algorithm with the regret associated with it. And the great thing about the perceptron algorithm is it's got like a finite regret. It actually makes a finite number of mistakes. And so, so what we can say is actually when we apply that to our queuing result, there's going to be a finite difference between the optimal policy, the queue length of the optimal policy, and the queue length of the policy that applies the perceptron algorithm to make the decisions about how to route the calls or how to deal with the calls which are calling up to the call center. Okay. So that sort of deals with that part. So it gives sort of slightly more involved example where you're applying sort of online learning and you're using it to make the scheduling decisions and to be able to separate out the different ways you deal with contexts of customers. Okay. This sort of leads on, finally, I'll go through very quickly, but to the next topic, which we're doing with Louis Seb, Rebuffy. So all of the things we did previously, basically getting small queue sizes is good. So you basically do the best learning algorithm you can do and then optimize that, and that sort of pushes things down, and that's good. So always low queue sizes was always a good thing. Okay. But however, like in certain settings, like you could think of something like revenue management and inventory control. If your inventory goes to 0, then that could be a problem. So having low queue size isn't necessarily always a good thing, particularly if you want to make sure you've got inventory available. Okay. So in prior examples, we want to learn and optimize the departure was sufficient and that low queue size was always better. But what if we want to optimize a different metric, such as revenue? How would you go about doing that, given the way that the queue size is evolving? Okay. So this is kind of very current and a little bit ongoing work, really. So just to briefly mention about revenue management. So kind of the modern things in the revenue management have been sort of like applying online learning algorithms, a bit like kind of like contextual bandits and things like this, but using pricing decisions rather than sort of selection decisions. So here at IID, each time you're going to receive some contextual information about someone's maybe gone on your website and they've filled in some data and things like this. Then you choose some price, the amount of money you're going to charge them for that product. And the combination of the context and price decides some input. And then as a function of that and some unknown parameters, we get some output. So if mu was just not here, then this would just be linear regression. And if the mu's here, maybe we could have like logistic regression or something like that if we had the logistic function here, where the logistic function would then say if we sell or don't sell the item, something like that. Okay, so we get some information back about the sales. So based on the volume of sales and the price, we get some revenue, which is the product of the volume of sales and the price, and we want to maximize that. Okay. So the kind of classical revenue management approach is like someone comes in, we get fresh context, we choose a price, we see if we sell the item or not, or some volume of the items or not, and then we get revenue. And then we try, and then what the kind of online learning kind of community there is trying to do is trying to basically optimize or try and estimate what this parameter beta is at the same time as making sure they perturb. So they need to perturb the prices enough to learn what the beta is, but they want the prices to narrow in on the optimal choice as quickly as possible in terms of the revenue. Okay. So it's got this kind of explore exploit type feature to it. So typical results look like this. You define the regret as the best revenue you can make compared to the revenue of your policy, which has to choose prices at each time and try to explore around the different prices. Typical kind of results that people use as kind of lie-in-way result, which says that if I apply sequential linear regression, the difference between my maximum likelihood estimator and the true parameter is essentially determined by the log of the maximum eigenvalues of the x's, or the design matrix of the x's divided by the minimum eigenvalue. And if you control that reasonably well, you can get these like order square root of t regret bounds. Okay. So lots of people like Arnold and Bohr and other folks like this have been working on that kind of stuff. Okay. So that's kind of the way the kind of learning theory works for kind of modern. So modern theory and revenue management and learning tends to have taken that approach. One of the issues is that the system refreshes at every round. And so essentially you get a new completely independently drawn IID customer at each round. But if you look at like older revenue management literature, what people tend to have done is say like, well, it's, you know, things from like airline pricing where the number of seats left on your aeroplane actually affects your price, or that you want to make decisions, but there's this inventory process moving around in the background. You want to let that influence your decisions, if you see what I mean. And so then you've got these parts of the process which are essentially determined by some sort of queue size mechanism or some sort of Markov chain mechanism in the background. Okay. So essentially inventory matters and influences prices. So we're kind of trying to we've been sort of coming up with like a formulation of that kind of revenue management literature where you still get an IID context. People turn up, you have information about what they want to buy, their search criteria and all the rest of it. You have some like inventory or some sort of process that's going on in the background, which is your sort of amount of stock that you have. You're going to choose prices, and your inventory level influences the prices you choose as well as who wants to buy it. Okay, so then you get input information, some of which is IID random variables, some of which is Markovian, but influenced by your pricing decisions. And then you've got stuff that's influenced by your pricing decisions, which you also need to learn about. And then you have the same thing, whether you sell something or not, is determined by all of these factors, essentially. Okay. And then based on that, you might update the level of inventory. So maybe some inventory departs, maybe you bring some more in, and then you receive some revenue based on the amount of items that you've been selling. Okay. And so essentially what we've been doing there is, it's interesting because you're not just trying to get low queue sizes. Low queues aren't necessarily good. You try to maximize some secondary objectives subject to trying to control the queue size process and the influences of that, and trying to learn the parameters associated with that and how that influences the system. And from a technical standpoint, it's sort of quite interesting because you're trying to get all these kind of matrix eigenvalue kind of bounds, but where rather than being like IID matrices, you're kind of adding on like Markov chains. So the sort of adding is sort of like a Markovian matrix thing. And you've got to deal with lots of things related to the mixing times of the Markov chains that you're dealing with as well. And it is in principle possible to get kind of similar types of regret bounds in that setting as well. So you've got sort of the inventory aspect as well as the IID context and all those kinds of things. Okay, and as predicted, I'm not going to have time to talk about topic number 5, so I'll stop there and stop for questions. So great, thanks, Jing. I'll take this as the first question.
Thank you, Neil. Let me just say let's thank Neil for his excellent talk. Thank you very much, Neil. I hope everyone joins me in this. Right, I wasn't interrupting you as you got a lot of questions as you went along, so I guess many people will be leaving now to other commitments. But if you have some time, Neil, and if
fine,
some time and want to ask questions, then please. I guess Jing, you already have your hand up, so if you'd like to ask a question.
Yeah. So I just have a quick question about the last example you talked about. So there, when you take the inventory into account, you're still just optimizing the pricing decision, or you're also optimizing some inventory control decisions there?
Yeah, so then what we're assuming here is essentially the pricing decision then might influence whether you make a sale or not, and that influences the inventory.
But you're not making decisions about when I should, let's say, replenish my inventory or things like that.
No, things like, well, for now at least, we actually leave things fairly abstract. We just say that there's some A decision, and the chain, the A influences the dynamics of the queue size process. But we kind of restrict things so that the A's kind of converge to some value, and so this converges to like just a normal homogeneous time Markov chain. And then we need that to be mixing in a nice way so that we can get all the eigenvalue bounds and get everything to learn properly.
I see. So I guess when there's no pricing decision, when there's just learning what would be a good inventory policy, let's say a base stock policy or something like that. There were some earlier work talking about using gradient descent type of a stochastic gradient descent type of idea to learn, say, what's the optimal base stock level. What you said here, is that similar, or it's because of you're looking at the pricing aspect, so it's actually quite different from?
I mean, if you don't experiment with the prices enough here, then you're not going to learn enough information. So you need to there needs to be some amount of price experimentation. But that means if you don't experiment with the prices, you don't learn the parameters associated with the prices. But also you've got to remember that the prices also implement the queue size and make things worse for you if you're moving the prices around too much as well. So there's this extra added fact that the movement in the prices are affecting the queue sizes and then kind of influencing things that way. So it's still a little bit work in progress at the moment. So we've got some results that kind of work out, and then other things that we want to kind of develop a little bit further. But yeah, and the other thing is we want to make sure that we're dealing with things in the contextual case as well. So that makes it a little bit different because there are things where people do like Kiefer-Wolfowitz and stochastic gradient descent and things like that, and they tend not to work when you've got these kind of contexts because they're kind of, at least for Kiefer-Wolfowitz, it's like more for like smaller parameters, so we got like a kind of smaller parameter range to work with, if you see what I mean. So wanted something where it's kind of like reasonably biggish kind of problem as well. So
I see.
Yeah.
I guess sorry, I don't know if other people have questions. I don't want to.
But from a technical standpoint, I just thought it's so interesting because it seems like a lot of the kind of learning revenue management stuff seems to be IID, and it's just interesting to see how it all kind of works out and to what extent the decisions that you make influence the queue sizes. So I wanted something independent. I didn't want like an MDP approach where you take exactly the queue size, you make a decision every time, but there's some sort of like macro level pricing decision that you make. And once you fix that, the queue sizes are essentially going to evolve. And then you just want to slowly adjust these parameters, and then you get, and then can you still kind of do the learning and earning side of it at the same time? And
So I will ask, getting a bit into the technical side. So your objective function or your loss function here is defined with respect to the stationary performance metrics, right?
Yeah, exactly.
When you do estimate the gradient information, I don't know if you take a stochastic gradient descent type of approach for this, but when you estimate the gradient information, because the gradient information is potentially coming from a Markov chain, so there is a it's intransient rather than stationarity.
Yeah, so here we're assuming that this mu function here, the mu function here is sort of known, and we're doing like a maximum likelihood estimation kind of approach, or what's called quasi-maximum likelihood estimation approach. We're not trying to estimate gradients or do any of that kind of stuff. We're assuming that the statistical model underlying it all is known. We know what that we can update to get the maximum likelihood estimator every time. So it's not going to scale like to the way gradient descent would, where you can kind of resample and things like this. And it's not going to be as online as those approaches, if you see what I mean. But the advantage there, I mean, the thing is, like, stochastic gradient descent doesn't work terribly well for these types of problems, because the kind of concentration bounds you have are much tighter for maximum likelihood estimators. So I think there isn't, and I've tried to mess and look in the literature there isn't like a result like this, I don't think, for stochastic gradient descent, where you're kind of adaptively choosing the X data, if you see what I mean, and then getting like quite, so this is sort of like what log T divided by T type bounds, and I haven't been able to find anything tighter than that in the literature for stochastic gradient descent, because remember, you do stochastic gradient descent, but that the decisions are, you're also choosing which data points you're getting next, if you see what I mean, as well. So you're kind of choosing the next function that you're getting in your stochastic gradient descent there as well, if you see what I mean. So that's one bit that changes slightly. Okay.
Thank you.
Thank you. Any other questions? We are very much behind, but I think we can, if Neil
Say
has
hi
time.
to Reba. Hi, Reba, as well. Good to see you.
David wants to ask a question. So.
Okay, hi, David.
Hey again, Neil.
It's asked me this slightly.
Right? So,
like it should worry about.
Right? It's too early in the day to pour myself a alcoholic beverage, probably, I guess. So, but let's see. Okay, I guess one quick thing but then I have some more interesting, like, philosophical questions. I guess I didn't follow the details of this last part, but I mean, like, there is work, something like this by, like, I guess Beryl Chen, probably, which, I mean, you probably know this work, right?
Yeah,
so,
yeah.
Okay,
that's probably the most similar thing I find,
cool.
And they've got like a Kiefer Wolfowitz type of approach to this, and it's like a non-contextual version, and that there's like an access control decision. They focus on access control itself. Yeah.
Okay,
so
so
I'm aware of that. Yeah.
So two kind of like high-level questions. So, okay, and again, just trying to take literally and think on what might be some good questions, the kind of queuing learning analog. So I guess, like, when we want to show something can be unstable in queuing, generally people are coming up with, like, an elaborate specific bad example that, like, makes it do poorly, I guess, right? That's like the general zigzags or something like this.
Yeah.
Right? I wonder, like, because again, if we, I think back to the question about, okay, what is the minimal information you might need, etc. And, like, right, like, metaphysically, there is a framework for answering that in learning, which is roughly you do this change of measure kind of stuff and show that you can't have done well across all these possible things in a precise sense, right? And I wonder if, as far as showing lower bounds in queuing, do you know of any papers that try to move beyond just showing, okay, like, for this policy, here's a bad example, etc., and actually maybe trying to use more of these information theoretic types of arguments which show impossibility results in learning?
In terms of queuing and learning, or just in terms of learning?
No, just straight up queuing, where you would just show, well, suppose we wanted to do well, no matter what the sequence is. But, in some sense, then you would kind of try to show that that's impossible, like, in an information theoretic sense, I guess.
I mean, the only stuff I know is, like, by Dave Germanik and
the adversarial queuing stuff.
Yeah.
Okay, and that's
I've seen, you know, obviously there are things of that nature, and whether it's decided, whether stability is decidable or not, and things like this.
Is some of that work stochastic in the adversarial queuing, or is it almost all kind of deterministic? I don't recall.
I think it depends on the system, but it tends to be deterministic. I think quite a few of the results I've seen tend to be more of that type. But I mean, yeah. But I think that's just because of the community it's come from being a bit more kind of like CS style, and it tends to be more like they bound the arrival rates and say there's like some window which you can make your adversarial decisions and deal with it that way. But then you can choose how much to put in or where to place the arrival and things like that. I mean that's the typical adversarial stuff. But in terms of just general impossibility results, yeah, I think it's hard to say. I mean, it's hard to say even when a queuing system's stable or not, and that seems to be a difficult question if you see it. It's hard to say like what parameters you can get away with and what you can't get away with, if you see what I mean. And then there's, you know, and then there's obviously a whole area of just what works well in practice, but we've got no idea why. Which is why I find it interesting, like the earlier stuff on the MaxWeight and the instability there, even doing like longest queue, which is like the simplest thing, like seems to be like a good idea, and then it doesn't work when you do it in the network in the wrong way. So I still find it hard.
So another question, and this again, maybe adversarial queuing does have some analyses that would give this, is I guess like, right, in kind of ML now, there's kind of a whole line of research around taking those original insights about no regret learning and trying to literally formulate the optimal minimax policy, whatever that would precisely mean.
Yeah.
And I wonder if in queuing, what do we know about literally minimax optimal policies in the adversarial setting in some sense?
That I'm not sure. In the stochastic setting, this Krishnamurthy paper that I mentioned earlier has some like lower bounds on what's the best.
They have lower bounds, but I mean, I guess I wonder if we have any sense at all in any meaningful cases about what like a literal minimax, you know, if you really wanted to just solve the minimax problem, what that would mean.
Yeah, it's difficult to say, isn't it? Because I mean, ultimately, like all the things that we end up saying are like asymptotically it's stable because we don't even know if it's stable or not. And then to ask the question of like, what's the best thing in terms of queue size? It's really difficult because like, you know, you're really kind of getting down to the minutiae of
so,
like
but that's a fair question, but I wonder, I mean, it's interesting to ask from a modeling conceptual point. In the regret setting, you could also have, I mean, if we make the analogy between stability and sublinear regret, right, then it's not clear why we should be able to talk about the literal minimax as a game regret thing, which they have.
Yeah.
Even though in theory, you might also say, well, but you could have linear regret. And so how can we even frame a minimax problem? Because you first have to worry about whether you're, you know, zero regret.
I mean, I don't see why not. I mean, it's an interesting research question, isn't it? Could you say what the best sort of queue size regret bound could possibly be in any scheduling setting or something?
You
like
have
this.
a past paper where you work out some explicit minimax solution for a queuing model, right? Or do you? Maybe I'm misremembering.
I'm trying to remember. I don't know.
Okay, I thought you look at.
I mean, there's this Blackwell stuff, which is the minimax theorem, which but it's not like what's that's different. That's like what's the worst algorithm the arrival process can do given the departure rate, rather than over the settable algorithms. You know.
Okay.
Yeah.
So you some short paper from a few years ago looking at kind of a adversarial queue kind of. Maybe I'm misremembering. It's your paper, so I assume I'm misremembering.
I mean, there have been other follow-up things on adversarial queuing in this kind of setting. I think like Modiano and people like this have worked a bit in that space, so there could be some things there of that type. I'm not sure. I'm not the most.
You must have been thinking your paper 2 queues with non-stochastic arrivals, I guess.
Yeah. I mean, there you basically say that the regret. I mean, it's basically this inequality that I had earlier, and I'm fairly sure this is pretty tight. Should be fairly tight that here. Sorry, this you know, that seems to dictate ultimately the behavior of the system, if you see what I mean, because if it, you know,
right,
so then it's sort of determined essentially, you know, it says less than or equal to, but I think that's probably pretty closely equal to. So, you know, essentially it depends on the regret over this interval from when the queue size is last empty to when to now, that ultimately dictates the behavior, if you see what I mean. So the better you can do on intervals of any given length, then the better you're going to do overall. So it's not over the whole sequence either. That's the other thing to say. It's not like the whole sequence of regret influences the whole performance. It's actually some like interval of time that seems to, which makes sense, because as soon as the queue size is emptied or anything like that's happened, well, all the things you've learned up until that point don't matter anymore in an adversarial setting. So obviously they do in a stochastic setting, they do.
Sure, that makes sense. So I guess I still don't like just I remember I've opened the papers a few times. So what exactly did Mike Neely show back when in those works?
I mean, he had some notion that you look at the sequence of arrivals over time and that you could adversarially change them. But I think that was a little bit wrapped up in these. He also had these kind of like utility maximization at the same subject to stability stuff as well. So it sort of gets a bit mixed up in that. There's a paper with the word like universality something something or universal something something of MaxWeight, and I think that's the most similar to that kind of Blackwell type stuff essentially. So I think that's the closest. I think I got the reference to that's in the paper with Kwang, I think. So I think that's the closest I've seen people sort of literally say like it's adversarially robust to the changing arrival rates in the sense that Blackwell would have meant it, if you see what I mean.
Yeah, I think I get
yeah.
that. I get that.
Yeah.